SpaceX just confirmed something shocking in their Flight 11 mission plan. They're deliberately stripping heat tiles from Ship 38, exposing bare stainless steel directly to re-entry temperatures exceeding 2,500 degrees Fahrenheit. For the first time ever, they're removing tiles from sections where there's zero protective layer between tile and hull. This creates the most extreme re-entry scenario Starship has ever faced. The reason? SpaceX needs hard data on structural limits to achieve full reusability. Every other space program protects their vehicles. SpaceX is stress testing theirs to destruction. Let's dive right in. Previous missions played it safer. Engineers removed tiles only from protected areas, sections with underlying thermal barriers. Ship 38 goes further by stripping tiles from zones where adhesive bonds directly to the stainless steel hull. No backup layer, no safety margin, just raw metal facing re-entry plasma at 2,500 degrees Fahrenheit. The official mission profile confirms these tests focus on non-critical sections, such as the aft skirt, rather than above the main propellant tanks. Smart risk management. They're testing areas where a burn-through won't destroy the entire vehicle, but even non-critical failures at Mach 20 can cascade. If plasma penetrates the wrong cavity, the whole ship could be lost. SpaceX's bet is straightforward. Stainless steel can endure more punishment than conventional wisdom suggests. If they're right, future starships need fewer tiles, cutting weight, maintenance costs, and refurbishment time between flights. If they're wrong, Ship 38 becomes a fireball over the Indian Ocean. Either way, they get data that can't be obtained any other way. The tile experiment isn't happening in isolation. Flight 11's complete mission profile validates multiple critical systems simultaneously, starting with Booster 15, which previously flew on Flight 8. This marks only the second time SpaceX will refly a Superheavy booster, launching with all 24 reused Raptor engines. No rocket this massive has ever been reflown before. Falcon 9 proved the concept works for smaller boosters, but Superheavy stands 70 meters tall and generates over 16 million pounds of thrust. The engineering complexity scales exponentially. After stage separation, Booster 15 tests a new landing sequence designed to become standard for Block 3 Superheavies. Current procedures use 3 engines for the final hover phase. Flight 11 introduces a 5-engine divert phase before transitioning to 3 engines for Gulf of Mexico splashdown. The reason is redundancy. During critical landing maneuvers, having 5 active engines gives the flight computer backup options. If one engine shuts down with only 3 running, you risk losing the vehicle. This becomes essential when SpaceX starts catching boosters regularly at Kennedy Space Center and offshore platforms. The new sequence proves the system can handle engine failures during the most critical phase of flight. Ship 38 also carries 8 Starlink simulators, dummy satellites matching the weight and dimensions of next-generation Starlink V-3. Flight 10 achieved the first deployment, but 2 units struck the doorframe during release, exposing clearance issues that would destroy real satellites worth millions each. Flight 11's refined mechanism validates whether Starship can handle operational Starlink launches as early as Flight 13. The economics are significant. Falcon 9 carries roughly 20 Starlink satellites per launch. Starship could deploy 100 or more. That's not incremental improvement, that's market transformation. Equally critical is the in-space Raptor relight test using header tank propellant. Ship 38 will shut down its engines in orbit, then restart them. This demonstrates Starship can perform controlled re-entry from any orbit, essential for missions beyond low Earth orbit. Without this capability, a Starship has one deorbit attempt. If that burn fails, the vehicle is stranded. More importantly, deep space missions require multiple burns: Earth departure, course corrections, Mars orbit insertion, and landing. Each burn demands engines that have survived the vacuum of space, extreme thermal cycling, and unpredictable propellant behavior. Flight 11's header tank test proves the entire propellant management system works under real conditions. Ship 38's descent includes what SpaceX calls a banking maneuver, simulating return-to-launch site profiles. This test is fundamental to Starship's operational future. Current flights end with Indian Ocean splashdown, half a world from Starbase. That's acceptable for testing, but operationally useless. You can't reuse a vehicle sitting in the ocean thousands of miles away. SpaceX needs Starship to return to the launch site, exactly like Falcon 9 boosters. The banking maneuver bleeds velocity through aggressive aerodynamic control. The spacecraft essentially skids sideways through the upper atmosphere, using its body as a massive air brake. This demands precise control at hypersonic speeds while plasma flows around the vehicle and potentially blacks out communications. Flight 11 validates the subsonic guidance algorithms before landing burn and splash down. Success proves Starship can achieve tower catch precision. SpaceX is already indicating Flight 13 could attempt the first ship catch, just 2 flights away from catching a vehicle the size of a 15-story building traveling at supersonic speeds. While the world watches launches, SpaceX is rebuilding the infrastructure that enables high flight rates. Flight 11 will be the last from Pad 1's current configuration. Immediately after, SpaceX tears down and rebuilds the orbital launch mount to match Pad 2's upgraded design. Pad 2 approaches operational status. The flame trench deluge system has completed multiple tests, some running nearly a full minute at increasing pressure and volume. The booster quick disconnect finished extension and retraction tests. Scaffolding is coming down. If Pad 2 goes operational by year's end, SpaceX will have 2 pads launching the world's most powerful rocket. Block 3 Starships starting with Flight 12 use Pad 2. This means SpaceX could launch from both pads, potentially doubling test cadence in 2025. At Kennedy Space Center, flame diverter buckets now sit in the LC-39A trench, the same pad that launched Apollo 11 and the Space Shuttle. The Gigabay is rising with steel columns going vertical. SpaceX is building industrial-scale spacecraft production at sites where NASA once hand-built rockets one at a time. The contrast reveals their fundamental approach: high flight rate, rapid iteration, acceptable failure. Flight 11 validates SpaceX's complete operational philosophy: booster reuse, proven; payload deployment, refining; in-space restart, testing; return to launch site, simulating; heat shield margins, stress testing. Each element builds toward the same goal: routine orbital access with aircraft-like turnaround. The same week SpaceX released this mission profile, Firefly Aerospace's test facility in Briggs, Texas exploded during a routine Alpha rocket hot fire. The destroyed booster was scheduled for Flight 7, now delayed to early 2026. For a small company competing with SpaceX and Rocket Lab, this hurts. But the explosion happened during ground testing, exactly where it should. The test system caught the failure before reaching the pad. Meanwhile, Italy's Avio signed a €40 million ESA contract to develop a reusable upper stage clearly inspired by Starship, complete with flaps, heat tiles, and methane oxygen engines. The scale tells the story. Starship stands 123 meters tall, targeting 150 tons to orbit. Avio's demonstrator will be 23 meters high, focused on cost-effective reusability. Europe is acknowledging what China already admitted. SpaceX changed the game. Reusability is now mandatory for commercial space. The rocket industry is dividing into 2 camps: those who test until perfect, then fly rarely, and those who fly often, treating failure as data. SpaceX is proving the second approach works at unprecedented scale. They've destroyed hardware. Flights 1, 2, and 3 all failed. But each failure generated insights impossible to obtain otherwise. Flight 11 embodies this philosophy: strip the protection, expose the weakness, measure what happens. If the steel survives, SpaceX unlocks faster refurbishment and higher flight rates. If it fails, they know exactly where the limit is. Either outcome has value. That's the difference between SpaceX and everyone else. So why deliberately remove heat tiles and risk a $100 million spacecraft? This is exactly why SpaceX is accelerating while competitors remain stuck in analysis paralysis. They're building a data library no one else can match. Every extreme test adds to their understanding of what's actually possible versus what engineering textbooks say is safe. What this means: by the time other companies develop reusable rockets, SpaceX will have flown hundreds of missions with operational knowledge earned through real flight data. If Flight 11 proves steel can handle more heat exposure, future Starships might need 30% fewer tiles. That cuts weeks off refurbishment time and compounds across dozens of annual flights. We're watching experimental spaceflight become operational infrastructure in real time. Flight 12 brings Block 3 hardware. Flight 13 might attempt the first ship catch. By 2026, Starship could be deploying entire satellite constellations and testing refueling depots for lunar missions. And this is just the beginning. Here's the question. If bare steel survives even brief re-entry exposure, could future Mars ships use a hybrid approach? Tiles only where critical, accepting some surface damage for massive weight savings? Drop your thoughts in the comments below. This is Space Hub. We break down the technical decisions that actually shape spaceflight's future. If this analysis added value, hit that like button. It helps us reach more space enthusiasts. Subscribe and turn on notifications so you never miss our coverage when Flight 11 launches October 13th. Comment below with your predictions. Will the exposed steel survive, or will we see Ship 38 become a fireball? The space industry is accelerating faster than ever. SpaceX's bet on the steel will be tested in days. And either way, we're one step closer to making space access routine. September 29th, 2025. Firefly Alpha explodes during a static fire test at their Briggs, Texas facility. The entire first stage is gone. The test stand severely damaged. This marks their second catastrophic failure in 6 months, following April's Flight 6 disaster. Stock plummeted 11% in after-hours trading. Lockheed Martin's payload survived, but they're now seeking alternative launch providers. With 2 consecutive failures, industry analysts are questioning, can Firefly recover, or will Alpha be permanently grounded? Let's dive right in. Let's start with the facts. Early Monday afternoon at Firefly's Briggs, Texas facility, the engineering team was executing a standard pre-launch procedure, a static fire test of the Alpha Flight 7 booster. This wasn't experimental. Static fires are industry standard. SpaceX does them. Rocket Lab does them. It's the final checkpoint before stacking the second stage and integrating a customer's payload. The setup was textbook. 4 Reaver 1 engines burning, RP-1 kerosene, and liquid oxygen, bolted to the test stand, generating thrust while the rocket stays grounded. The test verifies engine performance, fuel system integrity, and structural stability. Everything looked normal during prep. Then in a fraction of a second, catastrophe struck. The explosion was instantaneous. A massive fireball consumed the booster, sending a tower of black smoke into the Texas sky. Seconds later, a second blast followed, so powerful that security cameras at a nearby car dealership shook from the shockwave. Witnesses reported feeling the impact miles away. Fortunately, strict safety protocols meant no injuries, but the test stand took severe damage, and the entire first stage was destroyed. Firefly issued a statement within hours, confirming an event that resulted in a loss of the stage, but providing no root cause. That investigation is still ongoing. What makes this failure particularly troubling is the timing. This didn't happen during the high-stress environment of launch or flight. It happened on the ground, during a test specifically designed to catch problems before they become disasters. The market reaction was swift and brutal. Within hours, Firefly's stock plummeted more than 11% in after-hours trading on September 29th. But the financial damage extends far beyond that single-day loss. The destroyed booster represents tens of millions in lost hardware. The test stand will require extensive repairs, potentially months of work depending on the structural assessment. Alpha Flight 7, originally scheduled for October 2025, has been pushed back to 2026 at the earliest. In the commercial launch industry, every month of delay translates to lost revenue and eroding customer confidence. There's a silver lining worth noting. Because the explosion occurred before stage stacking, Lockheed Martin's payload survived intact. That's critical. Under their multi-mission agreement with Firefly, up to 25 launches through 2029, this was the third planned mission. The satellite is safe, but the launch timeline is shattered. Industry sources indicate Lockheed Martin is already exploring alternative launch providers, with SpaceX's Falcon 9 at the top of the list. When your anchor customer starts seeking backup options, that's not just a business setback. It signals a fundamental crisis in reliability. Here's where we need to address the uncomfortable reality. This is Firefly's second catastrophic failure in 2025. The pattern demands scrutiny. In April, Alpha Flight 6, dubbed Message in a Bottle, launched from Vandenberg Space Force Base carrying Lockheed Martin's LM-400 satellite. During flight, the second-stage Lightning I engine shut down prematurely. Mission failure. Satellite lost. Firefly's investigation revealed critical findings. The first-stage booster flew at a higher angle of attack than previous missions, exposing one side to recirculating hot exhaust from the Reaver 1 engines. This created flow separation and thermal damage to the booster structure. When the first stage separated, that structural damage generated a shock wave that destroyed the upper stage engine, killing the mission. Now consider the progression. Flight 6 failed due to first-stage structural and thermal issues during flight. Flight 7 exploded during a ground test, also involving the first stage and the same Reaver 1 engines. 2 failures in 6 months, both connected to first-stage systems. This isn't coincidence. It suggests potential systemic issues with either the Reaver engine design, manufacturing quality control, or testing procedures. Firefly's recent struggles have made them a target in the notoriously competitive space industry. At the Berkeley Space Symposium 2025 earlier this month, Astra CEO Chris Kemp, a former partner turned rival, launched a public attack on Firefly's engineering capabilities. "There is a company called Firefly. They went public," Kemp stated, barely concealing his disdain. "We bought the engine from them, and it was garbage. We literally could not get the same engine twice from them, and none of them matched the CAD. If you're in engineering, you know that just doesn't work." Kemp's comments ignited controversy across the space community. Firefly's leadership chose not to respond publicly, a wise strategic decision. But his criticism, however harsh, raises legitimate questions. When you experience 2 consecutive first-stage failures, when engines can't pass static fire tests, when boosters can't handle aerodynamic stress, these failures suggest possible inconsistencies in manufacturing or quality assurance. Kemp didn't stop at Firefly. He's also made inflammatory remarks about SpaceX,